Welcome, curious minds, to the deep dive. Have you ever really stopped to think about what's going on inside your head? When you're thinking or making a choice or just pulling up some fact. What if your mind isn't like one big boss calling all the shots? What if it's more like a bustling city?
Hmm.
Yeah, imagine a whole metropolis packed with tiny workers, each one doing its own little job. And your thoughts, your memories, even how you see the world, maybe that's all just a result of millions of these little agents working together,
Hmm.
cooperating, maybe even arguing sometimes.
That's more than just a neat metaphor. It's actually the really bold vision of one of AI's founding fathers, Marvin Minsky. He called it the Society of Mind. And his core idea, his really big argument, was that human intelligence, with all its amazing complexity, could actually emerge from what he called a federation of simple processes. Each process, each little agent, is pretty limited on its own, kind of basic maybe. But when they collaborate, that's where the power comes from. It was a pretty radical concept back then, really challenged how people thought about the mind.
And that's exactly what we're diving into today. We're going deep into Minsky's ideas. We'll unpack how he saw intelligence being built, breaking down these complex mental things into these separate agents interacting. We'll look at the impact this had, especially on early AI, the symbolic stuff. And then we'll jump ahead and see how these ideas still echo today, and maybe where they clash a bit with things like deep learning or these modern multi-agent systems. We'll also touch on the criticisms, right? Because it wasn't all smooth sailing. Some people talked about the messiness of real cognition, how the mind isn't always so neat and tidy. So if you've ever wondered how your own mind does all the amazing things it does, or maybe why AI, even now, finds some tasks that seem simple to us so incredibly hard, well, this deep dive should give you some surprising insights, maybe even a new way to think about intelligence itself, both ours and the artificial kind.
Yeah, and what's really fascinating, I think, is how Minsky's early thinking just laid so much groundwork. He identified core problems that AI researchers are still wrestling with today, even though the field went in directions he maybe didn't fully predict. A lot of the conceptual challenges he raised and the kinds of distributed solutions he imagined, they're still really relevant. It shows incredible foresight, really.
Minsky's vision, the mind as a federation of simple agents.
Okay, so let's really get into this core idea. Minsky saying the mind isn't one thing, not a single CEO, but this huge society of smaller, specialized agents.
Hmm.
I like that ant colony metaphor you mentioned earlier. Each ant does a simple job, carry a leaf, dig a tunnel, but together, boom, you get this incredibly complex colony behavior. How does that really work for something like, human thought? Is it just more ants?
The ant colony is a great starting point, definitely, because the big shift Minsky pushed for was exactly that. Away from the single boss idea towards a distributed bottom-up view. The magic, as you put it, isn't that any single agent is super smart? No, they're limited. Maybe one agent just recognizes, say, a vertical line, another recognizes a horizontal one. Pretty basic stuff. But Minsky's insight was how their collective action, how they work together through these complex networks, cooperating, sometimes competing, triggering each other. That's what generates complex thought, problem solving, understanding language, creativity. It emerges from the interactions. It's less about individual brilliance and more about the intelligence of the crowd or the swarm happening right inside your skull.
So it's about super coordination, not a super brain. Specialized labor. That sounds efficient. Did Minsky get specific about how they coordinate? Or how they handle basic stuff like memory?
Oh yeah, absolutely. He wasn't just talking in metaphors. He tried to work out the mechanics. For memory, he proposed this idea of K-lines. Now, these aren't physical wires, right? They're more like conceptual agents or maybe patterns of activation. Their job is to record the state of other groups of agents at a particular moment, like taking a mental snapshot.
A snapshot of activity, not just an image. Okay, so K-lines record the state. How does that become remembering something? Are we just replaying the snapshot?
Pretty much, that's the core idea. Minsky thought that when you later activate a K-line, maybe a smell triggers it, or a word it acts like a prompt. It tries to restore those other agents back to roughly the state they were in when the K-line was first created. It makes those parts of your mind do just what they did before. And then other parts of your mind react to that reactivated state as if the original event were happening again. So it's a reconstruction, not just playback. But, and this is crucial, Minsky pointed out that these memories are always incomplete. Always. Why? Because, he argued, no system can record every single detail of its own state.
Because it would need to be bigger than itself to store all that information.
Exactly. It's a fundamental limitation. Trying to record everything would be computationally impossible.
Yeah.
An overload.
Wow. Okay, so that inherent incompleteness, the fuzziness of memory, isn't a bug, it's a feature. It has to be selective. It's not like a perfect video recording we just replay.
Precisely. It's an active reconstruction each time, maybe even slightly different depending on your current state. It completely changes how you think about what memory is. It's efficient, it's adaptive.
So the messiness is actually a sign it's working well, filtering what matters.
You could say that. And Minsky didn't stop at memory. He pushed this agent-based thinking into really complex human stuff like emotions and attachment. He suggested that attachment bonds, those really strong connections we form, involve memory records, maybe like special K lines that form very quickly, but then are peculiarly slow to change. They stick around.
That makes intuitive sense for strong bonds. But why are they so sticky, so hard to change, even when maybe circumstances suggest they should?
That was the puzzle he was exploring. He connected it to things like imprinting in baby animals, where they form this super fast, almost irreversible bond. And then he described adult emotions, quite strikingly, as accumulating networks of mutual exploitations, like patterns of agent interactions build up over time, reinforcing each other, creating our emotional landscape. He even went so far as to suggest that after a certain point, trying to draw a hard line between emotional structures and intellectual ones is kind of pointless. You're just describing the same structures from different points of view.
Whoa. So emotion and intellect aren't separate boxes. They're just different patterns emerging from the same underlying society of agents.
That's the implication. Different configurations of the same machinery leading to different behaviors we label logical or emotional.
Okay, so agents handle deep emotional stuff. But what about everyday cognition, like visual ambiguity? When you look at something like a Necker cube and it flips back and forth, or seeing a drawing as maybe 9 small blocks or 3 arches or 1 big arch, how does the society handle that switching?
That's a perfect example. In Minsky's view, you don't have one vision center making a single decision. Instead, different interpretations mean different sets of agents are becoming active or maybe winning a competition. One group of agents is good at spotting small blocks. They fire up, you see 9 blocks. Then maybe another group, specializing in larger curves, gets activated more strongly, and suddenly you see the arches. Your perception shifts as different agent coalitions gain temporary dominance. The mind is actively building meaning, not just receiving it.
And this applies beyond vision too, right? He talked about common sense.
Yes, that huge ocean of background knowledge we all just have. His example was great. Hearing the sentence, Mary was invited to Jack's party. Instantly, the word party doesn't just get defined. It activates what Minsky called a party invitation frame. This frame isn't just the word. It's a whole network of expectations.
Like there will probably be cake, maybe music, gifts.
Exactly. Default assumptions kick in. Attendees, gifts, clothing, atmosphere, all this scattered knowledge gets pulled together instantly by this frame, this network of agents. It's how we fill in the blanks and understand things so quickly without having every single detail spelled out. It shows the power of these interconnected agent networks.
Minsky was also known for challenging other ideas, right? He pointed out a problem with theories that viewed the mind as more holistic or unified, the duplication problem.
Right. He posed this really tricky question. How can a mind compare 2 similar things? Let's say 2 slightly different ideas or 2 shades of blue. If the mind was one single holistic processor, how could it hold both ideas clearly in mind at the same time to compare them, without needing 2 identical copies of itself? It seems computationally impossible, or at least wildly inefficient.
You'd need 2 whole minds just to compare 2 thoughts.
Pretty much. He argued this duplication problem was a fatal flaw for most holistic theories of higher-level thinking. It strongly supported his view that you need to break things down. You need specialized agents that can represent different aspects or different ideas, and then other agents that can manage the comparison process. You don't duplicate the whole system, you activate the relevant specialists. About distributed processing, not monolithic duplication. That's the key for scalability and efficiency.
Early explorations and limitations.
Perceptrons.
Okay, so the Society of Mind was this big overarching vision. But before that, Minsky, working with Seymour Papert, did some really crucial, more focused work that had a huge impact, the book Perceptrons. This wasn't just a critique of early neural networks, it was a mathematical takedown, wasn't it? Showing their fundamental limits. It really was. Published in 1969, Perceptrons wasn't just hand-waving. It contained rigorous mathematical proofs. They showed, for example, that a simple, single-layer perceptron, specifically one where each unit only sees a small part of the input, a diameter limited, one literally could not learn to recognize something as basic as whether a pattern was connected or not.
Like telling if a line drawn on the input was continuous.
Exactly. To know if it's connected, you need a global view, right? You need to trace the path. But these simple perceptrons, by design, only had local views. They couldn't see the whole picture.
Makes sense. Like trying to read a sentence by only seeing one letter at a time.
Precisely. And maybe even more famously, they proved that these perceptrons couldn't compute parity. That's just determining if the number of active inputs is odd or even. Seems simple, right?
Yeah, sounds basic.
But they showed that for a perceptron to compute parity, at least one of its internal units had to be connected to every single input point. This meant that as your input got bigger, more pixels in an image, for example, the complexity just exploded. It became computationally infeasible very quickly for anything non-trivial. It wasn't just hard, it was mathematically shown to be impractical for scaling with that architecture.
So these single-layer machines had serious proven limitations. But surely people thought, okay, what if we stack them, use multiple layers? Did Minsky and Papert address that?
They did, yeah. They looked at what they called Gamba machines, which were basically like two-layer perceptrons. And they acknowledged that, theoretically, you could build a universal computer using the basic building blocks of perceptrons, these linear threshold units. But their main point wasn't just about theoretical possibility, it was about practicality. They argued that, at the time, there were no known effective learning algorithms for these multi-layer networks.
Ah, so you might have the bricks, but no blueprint or instructions on how to build the house or how to teach the builders.
Exactly. They were saying, sure, maybe it's possible in principle, but we don't know how to make them learn complex things reliably. That was a huge bottleneck.
So if you can build a universal computer from these parts, does that mean computation theory just boils down to perceptron theory?
Minsky and Papert argued quite strongly, no. And this is where they showed remarkable foresight, I think. They said something like, the computer is so much more than the sum of its parts that the computer scientists can afford to ignore the nature of the components and consider only their connectivity.
Wow. So focus on the organization, the architecture, the connections, not just the individual neuron or switch.
Precisely. It foreshadowed the whole idea of abstraction layers in computer science. We build complex software without needing to know the physics of every transistor. We care about the logic, the algorithms, the flow of information at a higher level. The whole is greater than the sum of the parts.
Now, this whole period, the late 60s, early 70s, it connects to this narrative of the AI winter, right? Minsky and others were famously optimistic back at the Dartmouth conference in '56. Did the Perceptrons book contribute to a cooling off?
Oh, absolutely. This is where it gets really interesting in terms of AI history. The rigorous limitations laid out in Perceptrons landed right when some of the initial, maybe overblown optimism was starting to fade.
Yeah.
It provided concrete mathematical reasons why AI was proving harder than some pioneers had predicted. This definitely contributed to the AI winter, a period where funding dried up, progress seemed to stall, and there was a lot of skepticism.
So it highlighted the gap between the grand vision and the actual capabilities of the tech back then.
Exactly. It showed that the ambitious claims needed to be tempered with a real understanding of the underlying limitations. It's a pattern, honestly, that we still see sometimes today with AI hype, right? Grand promises followed by a period of adjustment when the hard realities set in. Perceptrons was a major reality check for the field.
Minsky's influence and divergent paths in AI.
So Minsky's focus on agents, on frames, on breaking down problems, that really fit well with what became known as symbolic AI, didn't it? The approach that emphasized explicit knowledge, rules, logic.
It did, very much so. If you connect the dots, Minsky's ideas provided a philosophical and architectural underpinning for a lot of symbolic AI research. This approach centered on creating systems with explicit representations of knowledge, often using symbols that stood for real-world concepts or logical operators. The goal was often to mimic human reasoning step by step. You'd program the rules, define the concepts. Think of early expert systems, or those block worlds where a simulated robot hand manipulated simple shapes according to programmed logic. That was very much in the spirit of Minsky's agents handling specific pieces of knowledge according to rules.
But that approach had its limits too, right? It often struggled outside those carefully controlled block worlds. Dealing with the ambiguity and sheer scale of the real world was tough.
That's the common critique, yeah. Symbolic AI was very powerful and well-defined narrow domains where you could specify the rules and the relevant knowledge explicitly. But generalizing to messy, unpredictable reality proved incredibly difficult. How do you write rules for everything? For common sense, it became brittle.
And then, more recently, AI took a very different turn. We've seen this huge wave of success driven by, well, the descendants of the very things Minsky critiqued, neural networks leading to machine learning and deep learning.
Exactly. It's kind of ironic, isn't it? The contemporary successes in AI, the things grabbing headlines now, largely come from moving away from purely symbolic systems. The key difference, and it's a big one, is that these neural network systems are deliberately designed not to start with a representational system in that explicit symbolic way.
Hmm.
They don't begin with pre-programmed rules about cats or dogs or parties.
So how do they work?
Well, they essentially learn from data, massive amounts of data. They use algorithms like gradient descent to constantly adjust the connections, the weights, between their artificial neurons based on whether they're getting the right answer during training. They filter these unfathomable amounts of data, find patterns, and produce these really powerful outputs. And this same basic approach, learn from data, adjust weights, powers everything from chatbots like ChatGPT to image generators just by changing the specific network architecture and the training data. It's a fundamentally different philosophy from symbolic AI.
Let's make that concrete. Think about a convolutional neural network, a CNN, learning to see. How does that work? Does it have little edge detector agents like Minsky might have imagined?
In a way, yes, but they're not pre-programmed. What happens is the early layers of the CNN, through training, learn to detect very simple features, things like edges, corners, patches of color. You could think of these as emergent low-level agents.
Okay, so it learns the basics first, then what?
Then the middle layers learn to combine those simple features into slightly more complex shapes, circles, squares, textures. And as you go deeper still, the layers learn to recognize even more abstract things like parts of objects. Maybe a neuron learns to respond strongly to eyes or wheels or snouts.
And eventually whole objects.
Exactly. The final layers combine these object parts to recognize whole objects. Cats, dogs, cars, whatever it was trained on. This is called hierarchical feature learning. Deeper layers handle more abstract concepts. It's fascinating because it mirrors Minsky's idea of specialized agents in a hierarchy, right? But crucially, these agents, these feature detectors, emerged from the data. Nobody explicitly told the network, look for edges, then circles, then eyes. Concepts like cat just sort of crystallized out of the patterns in the training images. It's a self-organizing society, in a sense.
That's a key difference. Discovered hierarchy versus design hierarchy. So both approaches grapple with knowledge representation, how information is stored and used, but they do it very differently.
Totally different. Minsky's frames were about explicit structures, default values, symbolic links. Modern systems, especially those using deep learning, often represent knowledge implicitly through things like embeddings.
Embeddings, like word embeddings.
Yeah, words, images, concepts get mapped to points in a high-dimensional mathematical space. Their relationships, similarity, analogy, are captured by the distances and directions between these points. So the vector from king to queen might be similar to the vector from man to woman. Knowledge isn't stored in a rule. It's embedded in this geometric structure learned from data. It's powerful, but often much harder to interpret. It's less like a dictionary and more like a complex, high-dimensional map. It's a very different kind of representation than Minsky's symbolic agents.
The society of mind in modern context, multi-agent systems and beyond.
Okay, so even though deep learning took a different path representationally, Minsky's core idea of a society seems incredibly relevant to modern AI, specifically multi-agent systems.
Absolutely. You can draw a very direct line. Minsky's society of mind is pretty much the conceptual blueprint for modern multi-agent systems, or MAS. These are systems explicitly designed with multiple autonomous software agents that need to interact, coordinate, maybe negotiate to solve a problem or achieve a goal.
You give an example. Where do we see this in action?
A great concrete example is a self-driving car. Think about that autonomous taxi again. It's not one giant AI brain driving the car. It's constantly taking in this fire hose of data, gigabytes per second, literally from cameras, LiDAR, radar, GPS, accelerometers, all sorts of sensors.
Okay, massive input.
Right. And then you have numerous distinct software modules. You can think of them as agents processing this data in parallel. There's a perception agent figuring out that's a pedestrian, that's a red light. There's a localization agent figuring out where exactly am I on the map. There's a planning agent charting the path. There's a control agent handling the steering and braking. Each agent has its specialized job, its limited scope, but they have to communicate constantly and coordinate flawlessly to produce that smooth, competent driving behavior. It's a textbook example of an engineered society of mind.
That makes it very clear. But just like any society, getting all these agents to work together perfectly must be a huge challenge, especially as systems get more complex. I read about this thought experiment, Prometheus, this powerful AI that had trouble ensuring all its parts spread across the globe were actually working towards the same goal, a self-control problem.
That's a perfect illustration of the challenge. It raises this fundamental question, especially for AI safety. How do you guarantee alignment and coherence when you have potentially thousands or even millions of semi-autonomous agents? How do you prevent mind fragmentation where different parts start pursuing conflicting goals?
How do you prevent that?
Well, it's a major research area. AI safety researchers talk a lot about collective action problems. This is where you have multiple rational agents, each acting perfectly logically according to its own programming or self-interest, but their combined actions lead to a terrible outcome for the system as a whole, an outcome none of the individual agents wanted.
Like each agent optimizing its own little piece, but breaking the bigger picture.
Exactly. Think of optimizing traffic flow in one neighborhood so well that it gridlocks the entire city. Minsky's model really forces us to think about these coordination and alignment issues. How do you ensure the society acts cohesively and beneficially? It's a huge deal as AI gets more powerful and distributed.
Minsky really wanted to understand the details, right? The microstructure of cognition. He wanted to open the box and see the gears, the agents. But with deep learning today, we often face the opposite, the black box problem. We know they work, often incredibly well, but we don't fully know why or how.
It's a stark contrast, isn't it? The quote that we cannot discover all the facts about the contents of the machine learning system's classifications simply by looking at the internal programming really hits it home. You can look at the billions of weights in a large language model, but that doesn't tell you why it generated a particular sentence or how it understands a concept. It's not like Minsky's vision where you could hypothetically isolate an agent and understand its specific rule or function.
So how do we make sense of them?
We often resort to what's called anthropocentric abstraction. We try to map the system's behavior or internal states onto human-like concepts. We might say, this part of the network seems to detect faces, or we ask, what does the output of this stop sign detector mean? But that meaning isn't always inherent in the system itself. It's layered on by us, the programmers, the users, based on the task and the context. It's an interpretation. This lack of true intelligibility is a massive challenge scientifically, ethically, and even legally, and it's quite far from the transparent, dissectable mind Minsky hoped to model. We have these powerful intelligences we don't fully understand.
Critiques and remaining questions.
So Minsky's society of mind is elegant, it's influential, but reality is often, well, messy. Both human minds and even the AI systems we build don't always fit neatly into these frameworks, do they?
Not at all. The messiness of real cognition is a recurring theme. And one area where this really comes up is prediction, especially predicting human behavior. There's a strong argument some people make that predictive AI, particularly for social outcomes, not only does not work today, but will likely never work. The reasoning is the sheer inherent difficulty, the complexity, and perhaps unpredictability of human behavior.
You mean even with more data, faster computers, we might just hit a wall?
That's the concern. Unlike predicting planetary orbits, where the physics is well understood and the system is relatively stable, human behavior is influenced by so many hidden variables, emotions, context, maybe even free will. It's just fundamentally different. Can a society of simple agents, even a vast one, truly capture that kind of complexity and unpredictability? Or does it require something more? It's a deep question about the limits of computational modeling when it comes to humans. The messiness might be irreducible.
That definitely highlights a potential gap. And speaking of gaps, we touched on AI hype earlier. Minsky was a visionary, no doubt, but AI history is full of these cycles, right? Big predictions.
Oh, yeah. Jeff Hinton's prediction about radiologists becoming obsolete in 5 years is a classic recent example. These things create this ever-receding horizon of the future, where true AGI or other transformative breakthroughs always seem just over the next hill.
It makes you wonder, how do we sort the real progress from the AI snake oil, as some call it?
That's the million-dollar question, isn't it? And it's getting harder. We have the reproducibility crisis in AI research, where studies find the small coding errors or variations in training data can completely change the results, sometimes inflating performance claims. It really urges extreme caution. We need rigorous validation, independent testing, and a healthy dose of skepticism about headline-grabbing results. It's a far cry from the kind of clear, understandable, dissectable agents Minsky was aiming for. The current reality is often complex, opaque, and sometimes fragile.
Even going back to the connectionist ideas that followed Minsky, like in the parallel distributed processing work in the 80s, researchers themselves pointed out limitations. They talked about the type token problem, and interestingly, the need for something more like an extra evaluative structure, something to oversee the rest.
Yes, that's a crucial point. It's like Minsky's society might need well, not a king, but maybe a parliament or a Supreme Court. It echoes this deep need for coordination, governance, and evaluation within this system. How do all these distributed agents or all these interconnected neurons arrive at a shared sense of what's true or right or aligned with the overall goal?
Without that higher level judgment, things could go off the rails.
Potentially, yes. How does the system evaluate trade-offs? How does it ensure ethical behavior? How does it maintain coherence? Just having lots of specialized parts isn't enough. You need some mechanism for oversight, judgment, maybe even self-correction. This remains one of the absolute central challenges in AI alignment and AI ethics today. How do we build that evaluative structure into increasingly powerful AI systems? It's perhaps the biggest remaining question, and Minsky's framework, by highlighting the distributed nature, actually helps us frame why it's so hard. Outro.
So we've really taken a journey through Marvin Minsky's incredible concept, the Society of Mind. We've seen how he broke down intelligence into these interacting agents, thinking about everything from K-lines for memory to frames for common sense. We looked at his early, impactful work on perceptrons and how his vision both shaped and, in some ways, contrasts with where AI has gone since with deep learning and modern multi-agent systems.
Yeah, and Minsky's insights, they really do hold up, don't they?
Yeah.
Even the critiques and the problems he highlighted are still so relevant. And, while symbolic AI and connectionism, rule-based versus data-driven, seem like opposites sometimes, maybe they're just different angles on the same basic puzzle. How do you get complexity from simplicity? Perhaps the real answer, for minds and for future AI, isn't strictly one or the other. Maybe it's a mix, a blend of both approaches working together. Agents that learn, but also operate within some kind of guiding structure.
So here's something to think about as you go about your day. When you're thinking, solving a problem, even just remembering where you left your keys. Pause for a second. Is your mind really that single, unified commander you might imagine? Or could it be, as Minsky suggested all those years ago, this incredibly busy, dynamic society inside? Countless tiny specialists all working together, sometimes smoothly, sometimes maybe bumping into each other, to create the amazing, complex, sometimes baffling experience of being you.
What part of Minsky's vision resonates most with you? How does it change the way you think about intelligence? Whether it's in your own head or in the machines we're building, it certainly gives you a different perspective.